Hello, ladies and gentlemen. I hope you're doing well today. My name is Daniel Wilson. I'm a PhD student at Liberty University. I'm working under Dr. Wayne Strasser and part of the Fluid Research Group. The title of my talk today is From Waste to Power, Pulsing Biosludge Atomization for Efficient Energy Conversion. We'll dive into the details of that in just a minute, and hopefully you'll learn something new. So let's get started. The goal of our research is efficient conversion of human waste to usable energy by injecting atomized biosludge into a boiler. So big picture, we're going from human waste, which is a problem, to usable energy, which is a resource. Now, biosludge here just refers to the processed human waste sludge, which is the output of a waste processing facility. The boiler is our energy harvesting equipment, and we atomize the biosludge, which is just breaking up the bulk fluid into smaller droplets. This is important because it provides a high surface area to volume ratio for drying and combustion. Our work specifically focuses on computational demonstration of an atomizer design, which can effectively process highly concentrated non-Newtonian biosludge. So we're using computational fluid dynamics, or CFD, to model and optimize the atomization process. Now, why is this important? Well, there are other methods of energy conversion, such as composting, digestion, gasification, pyrolysis, but these all have various disadvantages, some of which are dilution, energy-intensive drying operations, creation of greenhouse gas. So with our process, we're using a highly concentrated biosludge and directly injecting that into the boiler, which gets us several advantages, including increased conversion efficiency, reduced water usage because we're not diluting the biosludge, and reduced fossil fuel emissions because we're decreasing the transportation load. In the end, we actually are addressing 7 global issues which have to do with sanitation and energy. Fossil fuel scarcity, because this is an alternative energy source. Clean water shortage, because it uses less water. Greenhouse gas reduction, because it doesn't create a greenhouse gas. Undersized waste management facilities. Food safety and disease control, which are both sanitation issues. And life-saving energy production in developing countries. Now, for our atomizer design, we are working with a twin fluid atomizer with steam as the assisting gas. So this is illustrated in the diagram there. This is a typical twin fluid atomizer where steam's on the outside, biosludge is in the middle. And the steam shear, illustrated in blue, creates biosludge instabilities that then lead to droplet formation down the line. Steam is good as an assisting gas because it reduces biosludge viscosity and therefore creates effective atomization. However, steam also reduces boiler efficiency because it's a heat sink and a source of non-combustibles. Therefore, we want to seek a balance between minimal steam usage and effective atomization. Now, we assess 3 general designs and the atomization quality resulting. The first is the typical design, which you just saw, where steam flows on the outside. This had the worst atomization quality. A little better is, actually significantly better, is an inverted design where steam flows on the inside. But even better still is an inverted design with steam on the inside and forced interaction. So this is a little extra length on the atomizer that forces the steam and biosludge to interact and produces better atomization. Here you see our current CFD model for the atomizer, where biosludge is red coming on the outside, steam is blue coming in the middle, and you see the breakup of the biosludge into smaller droplets, which is the atomization there on the right. This is the forced interaction region, that extra little length that just forces the steam and biosludge to interact and help the atomization process. Now keep in mind that this is a 1/32 wedge model with periodic boundary conditions, and it's a coarse mesh with no grid independence, and it's only for controller proof of concept. So we'll talk about controllers later, but this is a coarse mesh just for the controller proof of concept. Now, an interesting thing happens when you invert the feed and have the forced interaction design. The interfacial unsteadiness actually creates a pulsing flow, which amplifies the growth of instabilities, resulting in better atomization. You can see this in the animation here, where blue is the biosludge, and you can see it kind of coming out in bursts or pulses. It's the pulsing nature of the system. Keep in mind, there are rings in addition to droplets there. That's just because we have a wedge model that's been rotated around for a full 360 degrees. Now we run into a problem because the viscosity of biosludge varies widely. A high viscosity leads to a large pressure drop for the biosludge, restricting the flow and leading to poor atomization quality and also strain on the pump. So we introduce what we call smart atomization, which adjusts the flows of biosludge and steam to account for dynamically changing fluid properties. We do this with two proportional integral derivative controllers. These are PID controllers, very common in industry. And a PID controller just adjusts one parameter to keep another parameter constant. So our first controller is the biosludge flow controller. This automates the flow of biosludge based on pressure drop. So the objective here is to maintain constant biosludge pump requirements, which is just the pressure drop for varying viscosity. The second controller is a steam flow controller. This compensates for the phase momentum ratio as the flow of biosludge is changing, and it automates the flow of steam based on droplet size distribution. Here, droplet size distribution equates to atomization quality. So the objective of this controller is to maintain atomization quality for varying viscosities. Now, the PID control algorithm that we implement is the discrete velocity form, where you're calculating the change in controlled variable P. And this is demonstrated in the equation there. E is the error, just the difference between the measured value and the set point, which is where you want to keep that measured value. N is the timestamp, delta T is the sampling time, which is the time over which the measured variable is averaged, and three controller constants are there: the gain, integral, and derivative. These can all be tuned for performance. Now we implement this algorithm as a user-defined function in ANSYS Fluent. That's a UDF. It's a subroutine to modify the software to do custom functions. In this case, adding two controllers. We add protection to keep the mass flow rate from going below zero, so the controller can't set it below zero, and outlier values are not included in the averaging process to keep the controllers stable. So we run two tests to test these controllers, and for each of these tests we increase the viscosity of the biosludge from 0.05 to 5. That's a 100-fold increase. So the first test involves constant steam flow and the biosludge flow controller engaged. So one out of the two controllers engaged. The second test involves both the biosludge and steam flow controllers engaged, both controllers engaged. The viscosity is increased, as I said, 100-fold, 0.05 to 5 kilograms per meter second. The dashed red line demonstrates where that happens at T, or time equals 0. The pressure set point is 110 kilopascals, demonstrated by that black line. And note that the conditioned pressure here is just the moving average of the biosludge inlet pressure, which resets each sampling period. The biosludge inlet pressure is representative of pressure drop because the outlet is set to a constant pressure. So if we look at these plots, the pressure starts off at about 110 kilopascals, and then when the viscosity jumps up, the pressure jumps up accordingly, as we would expect. But then the biosludge mass flow rate is decreased, which is shown on the right-hand plots. And this brings the pressure back down to the set point, as it should. So both tests are doing essentially the same thing, which is what we expect. Pressure comes back to set point. So this is good. This is demonstrating keeping the pump requirements constant with a constant pressure drop. Now, for the second part of this, we'll look at the D32 or droplet size. So again, first test, constant steam flow with Biosludge flow controller. Second test, both controllers engaged. Viscosity jump is illustrated with the dashed red line like before, and the D32 set point is 0.00125 meters, shown with the black line. And that's only relevant for the second test where the steam flow controller is actually engaged. The D32, or the conditioned D32 rather, is the moving average of the D32, or the solder mean diameter. This is just a droplet size average, which resets each sampling period. And remember, droplet size equates to atomization quality. So what do we see from these plots? Well, for test 1, the droplet size is about 0.00125 meters, hovering around there before the viscosity increase. Then afterwards, it increases and varies pretty widely. So atomization quality decreases. But for test 2, the coupled controller system maintains the droplet size pretty well. It's keeping it at the around the set point of 0.00125. And so we're maintaining a relatively constant atomization quality. So this test is demonstrating the efficacy of the coupled controller system to maintain atomization quality for a 100-fold increase in biosludge viscosity. So now just some concluding thoughts to wrap up. Remember that our objective is efficient conversion of human waste to usable energy by injecting atomized biosludge into a boiler. Our motivation is really environmental stewardship, particularly the issues of energy and sanitation needs. And our valuable contributions so far are showing the inverted forced interaction design improves atomization quality, and demonstrating that the coupled controller system can maintain relatively constant atomization quality for a 100-fold increase in biosludge viscosity, therefore demonstrating the efficacy of the coupled controller system. For future work, we'd like to optimize the injector geometry for minimal steam and effective atomization. Thank you so much for listening to my talk. I really appreciate your time. I'd be happy to address any questions that you have, and I hope you learned something new and really appreciate it.